Zoom. It is my great pleasure to welcome you at this 176th Cutter Lecture. My name is Bert Hoffman. I'm the chair of epidemiology here at the Harvard Chan School. And the Cutter Lecture has been given once or twice a year since 1912 under the terms of the bequest of John Clarence Cutter, a graduate of Harvard Medical School. It's the oldest lecture series in epidemiology and preventive medicine worldwide, always presented under the auspices of the Department of Epidemiology, first until 1948 at Harvard Medical School, and since then at the Harvard School of Public Health. I also welcome the hundreds of you who are on the live stream specifically. Thank you very much for joining us. And then I go to today's Cutter lecturer, Dr. Julia Pearl. You see him upstairs. Dr. Pearl is professor of computer science and statistics at UCLA. He directs the Cognitive Systems Lab and conducts research in artificial intelligence. He is an author of quite a number of books, the last one being The Book of Why. Many of you may have seen that. He's a member of the National Academy of Science and the National Academy of Engineering. It is my great pleasure, not only that, it's a great honor for us, Judah, that you will present the 176th Cutter Lecture from LA, as you see. Thank you for doing this. You have chosen as a title, The Science of Cause and Effect, from Deep Learning to Deep Understanding and Personalized Decision-Making. Dr. Julia Pearl, the Zoom floor is yours.
Mine. Well, thank you very much for introducing me and for giving me the opportunity to address my old friends in epidemiology. I always said that epidemiology is one of the first discipline that has recognized the benefits of causal inference in general and graphical approach to causal reasoning. And it is also my great pleasure to reconnect with my old friends, Jamie Robbins and Hernan, with whom I did some early work as far back as 1984. And I just discovered that the paper we wrote together with Sander Greenland on the graphical approach to epidemiology has received the highest number of citation of all my papers, about 5,000 citations, discounting my books. Okay? So it's a great pleasure for me to do what? To do two things. Number one, to submit a progress report of what I have been brewing in my little corner, in my little cubicle, and also to outline some of the idea that I think should be adopted in epidemiology and in preventive medicine. So you see that I have a secondary title here, from deep learning to deep understanding and personalized decision-making. I'll elaborate on what I mean by that, and you can see it's quite a sweeping statement to go from to talk about deep understanding. And indeed, this is the main topic of my lecture. To understand what it means for a machine to understand. So understanding is the focus of my lecture. Here's my outline. First, I would like to apologize for saying the words new science and why we need a new science to answer causal questions. Of course, if we talk by causal question, we have to define what we mean by causal question, and then I'll present some of typical causal question, and present what I consider to be the fundamental laws. Some people call it double helix of causal inference, and then go through 7+1 pillars of causal wisdom. These are the ramification of what the fundamental law implies. These will be tools of causal inference that allows us to do today things we couldn't do yesterday. I will elaborate on how they impact several application area and how they lead to personalized decision making, which will be the last topic I want to talk about. Okay, so what is the science of cause and effect? First, what is science? In my little corner, being trained as a computer science, a science is a transformation from a query to a solution subject to several input and certain constraints. So here we have a query, the thing I want to estimate. I have a model of the world. At least I have an idea of how the world operates, but I do not have I don't have exact knowledge of that model. All I have is a partial model, some ideas of what the model contains. So this is my perception of reality. You see that this box, which I call calculus, has three inputs. One of them is the query, what I want to estimate. Second is my partial model of the world. And the third is data, including the method of collecting the data. And here we have a calculus. These are the constraints, the principles by which we want to uphold. Outcome a solution. What is the solution? Estimand. It will be the estimand of the query. Good. That is a basic principle here. And now I have to, I owe you a definition of causal questions. So some typical causal question. One, how effective is a given treatment in preventing a disease? That obviously is very clear questions in the Chance School. And number two, was it the new tax break that caused our sale to go up or our marketing campaign? Notice that I have a yellow highlighted here relationship, which I will apologize for later. What is the annual healthcare cost attributed to obesity? Can hiring records prove an employer guilty of sex discrimination? Has a lot to do with the recent emphasis on fairness. I'm about to quit my job. Will I regret it? And this is a personal decision making, you see. I know something about myself. The fact that I'm about to quit my job is an important information. Will I regret it? So when I highlighted this yellow relationship, I did it because they signals to you a relationship that cannot be articulated in the standard grammar of science. By standard grammar of science, I mean the science in which we see the equation of physics, because the equation of physics are married to the equality connective. So if in yeah, I'm missing a slide here, but I'll make up for it. The equations of physics are married to the equality. So if y is equal to ax, and then x is equal to y over a, whatever you can get moving from x to y will allow you to go from y to x. We are missing here the directionality that all these relationships abide for. So if I have for instance, I give you an example. If we have a relationship between the atmospheric pressure and the deflection of the barometer, we write it as deflection equal to a function of the atmospheric pressure, and not the other way around. You and I understand that there is here a directionality, but this directionality is buried, hidden, eliminated once we are using the equality sign. So everything I'm going to do here is can be looked at as an attempt to replace the equality sign by a assignment. In computer science, the assignment operator replaces the equality operator and gives it directionality. If I see a certain register containing item X, I can take it and assign it to another register that will now have the content X. It's an assignment, and therefore it is directional. So everything I'm going to say now is really an attempt to overcome this deficiency of the equality sign. Here is what I consider to be the two fundamental laws of causal inference. This is the law of counterfactual or interventions, and it has to do with something which we call M model. This is a collection of functions where a variable is looking into other variables, and nature assigns a value to one variable depending on the total values currently assigned to other variables in the domain. So this will be the notion of M model, in which it's a collection of functions simply telling you who is listening to whom. And that equation tells you that if you want to find the counterfactual, what the outcome y would be had variable x been small x for a certain unit u, all you have to do is take the outcome at a mutilated model M. Take M, mutilate it in a certain way, and the outcome y at the mutilated model is equal to what you are seeking, namely the counterfactual. Tied with that is the law of conditional independence, which can be derived from that, but still I put it up as a miracle because it's so useful that it deserves a name as one of the fundamental laws. It gives rise to, why I call it a miracle, because it gives us the ability to test models. Separation in the model means independence in the distribution. I now go to, just exemplify it. Here is a model, collection of functions. W3 is listening to X. X is listening to W1 and Z2 and Z3 and so on. You want to find the counterfactual, namely y sub x. What y would be had x been small x, all you have to do is mutilate this model, cut down the arrows going into x, substitute the function x is equal to function of w1 and w3 and z3, substitute it by a constant, and that's it. The value that you will find here is equal to the counterfactual. It's so easy. It's embarrassingly simple to compute counterfactuals. Now, what does it tell us? Oh, I'm listening. I need to raise this a bit. This is the second law. How to read independencies in a graph. I think most of the audience will be familiar with that, so I'll quit it because you have been students of Jamie and Hernan, and you probably have listened to their teachings, so you know how to compute, how to read independencies in the graph once you have the structure of the graph. You simply, that is a summary of a collection of functions. The functions are unknown, but regardless of the nature of the function, and regardless of the distribution of these u variables, if you have, if the u's are independent, then the observed distribution must satisfy the constraints. Every missing arrow here implies a certain independencies. Here's a missing arrow, it implies a certain independency. Here's a missing arrow, here's another one, where is it? Hop, 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 too fast, too fast. Anyhow, every missing arrow implied a certain independency. Okay, I go quickly over that, and I go to the three-level hierarchy, which some people call a ladder of causation or a DNA. Well, why is it DNA? Why is it so important? Because it tells you what information you need for every type of query. On the bottom, we have association, simply probability. If we observe something, what can we infer about something else? Back and forth in time. Intervention, if I want to do something, what can I expect? This is the intervention part. And the counterfactual level, which is accounting for understanding, this is imagining or introspection or understanding or computing the causes of effect. And it's and my now definition of understanding is a system that can reason on all three levels of the hierarchy. The capacity to answer queries on all three levels is what I define to be an understanding. Okay, I'm now going to the 7+1 pillars of causal inference. These are the ramifications, and I emphasize all these are derivatives of the first law of causal inference. Tool number one, encoding causal information in transparent and testable way. And that's not knocking, because the emphasis is on transparent, which means that the assumption that you make must be defensible and testable. Tool number two, predicting the effect of action and policies. We talked about it already. Computing counterfactual and finding causes of effect. This leads to question of attribution, explanation, or susceptibility. Tool number four, computing direct and indirect effect, which we call mediation. It plays an important role in discrimination, inequalities, and fairness. Tool number five, integrating data from diverse sources. We call it fusion, transportability, or transfer learning in the circles of computer science. They call it transfer learning. Extremely important, especially when we're talking about also, oh, okay, in the statistical circle, they call it meta-analysis. But it's much more than meta-analysis, because when you have information coming from diverse sources, you must understand the reason for the diversity before you can do a combination of data or fusion. The last one, unfortunately, I have this covered here. I don't know how to. Oh, I can move it. Good. I'll move it here. Okay. I hope it shows. Okay. And from here we go to personal decision making, which I'll devote at least 5 or 10 minutes at the end. Stop me when I'm going over time. Okay. Okay, so here's a bit of history explaining what happened in the relationship between graphs and probability. I'll skip on that history because it has to do with the realization that the axioms of conditional independencies in probabilities share a lot with the axioms of graph intersection in graphs. That is a reason why we have a marriage between these two seemingly unrelated mathematical quantities. One is probability. The other one is graph. Pillar number 2, control of confounding. That I think I should go quickly because that is really the essence of confounding, and it was. Oh, I'm sorry for that. I should have prepared it in time. Okay, here we are. Okay. So this question that has been at the core of epidemiological debates for maybe 4 or 5 decades, okay, has been completely demystified and reduced to a game. It leads to a backdoor adjustment for covariance, or front door and other doors, or do calculus, which is complete in the sense that we can now predict the effect of policy intervention whenever it's feasible, and whenever it's not feasible, the system can come out and tells you you haven't got enough assumptions. Pillar number 3 is the algorithmization of counterfactual, and this is all contained in the first law. Nothing to add about it, but it leads to estimation of causes of effect or attribution, which is something unique that has not been. I wasn't able to answer this question before the advent of the science of cause and effect. So it leads to things like that. Your Honor, my client died because he used this drug, and you see that the court is using counterfactual terms to define the condition under which penalty should be assigned to the accused. The court must decide if it's more probable than not that Mr. A would be alive but for the drug. So here you have the notion, the legal notion of but for, which is now can be formalized, algorithmatized so badly that you can come out with a guilty sentence under certain conditions when you combine the data. Mediation analysis, given data and model, unveil the and quantify the mechanism that transmit changes from a cause to its effect. And we have now a graphical representation of counterfactual, which tells us when direct and indirect effects are estimable from data. This is really the idea that was first articulated by Robbins and Greenland. But once we have a symbolic system, we are able to come out with conditions under which it is estimable and when it is not estimable. And we currently have a complete solution for this problem. I will quit here any discussion of mediation because we must go to pillar number 5, transfer learning, and look at this question. The task is a machine trained in one environment finds that environmental conditions changed. When and how can it amortize past learning to the new environment? And the solution now is complete, available. It has to do with selection diagrams, which tells us the reason for the change. Once we have a model for the reason for the change, we know how to combine the changes, how to combine the available data and come out with a conclusion which has to do with perhaps a totally different environment and totally different condition under which we want the solution to hold. It includes the problem of selection bias. Right. So the data to illustrate it to you, look at the here, the problem here where I just outlined a collection of data obtained from various sources. Some is in New York, where we have rich lawyers, in Los Angeles, where we have younger population, in Boston, here are the rich lawyers, okay? And San Francisco, Texas, each environment has a different characteristic, a different idiosyncratic character of the population, and we want to come out with the causal effect of X on Y in Arkansas, which is not even included in this environment. And this is totally bewildering and hard problem. But once we put it into a graphical notation, and where the graphs indicate the reasons for the change, then we can combine them, fuse the data, and come out with a solution. I'm going to pillar number 6, missing data, not elaborate on that, because only to say that in some circles, in statistical circles, it has been a mantra that causal inference is a missing data problem. No, missing data is a causal problem. And we are not getting anything by saying that it is a missing data problem until we understand the reason for missingness. And once we understand the reason for missingness, you can read the paper by Mohan and myself in, I believe it is the Annal of Statistics. Okay, so we can get an answer to the question is, can you find out the, here, let me say, can you estimate the probability distribution or some property of the probability distribution had the data not been missing, as if the data was not missing? And that is now we have a complete solution, and we can detect when missingness model is testable and when it is not. Okay, let's go over to the next one. Causal discovery. I will not elaborate because this is the work that has been done mainly in Carnegie Mellon, and they have a beautiful extensions of the old attempt to um, um, to discover set of graphs which are compatible with the data available. And sometimes from the set you can get conclusions which are valid for all the sets. And so I will only say that my recent discussion with business people has been surprising to me, that all of them are using causal discovery to for as a working principle. Okay? And once you have a causal graph generated by the data without any assumption whatsoever, okay, you can do a lot of things. I will not elaborate here, but go to the next one, which I think is important for the future of healthcare science. Personalized decision making. What do we mean with it? We mean we want to find out the probability that a given individual, you, would benefit or be harmed by a given treatment X, as opposed to the average recovery rate in the subpopulation which resembles the individual. So look at the symbolic distinction between the two. Here we want a probability of benefit. Namely, we want to find out, given the characteristic of individual U, I want to find the probability that Mr. U will recover if receiving a treatment and will not recover if not given the treatment. Compare it to the average treatment effect, which is the probability, the expected value of this difference. Again, conditions on the characteristic. To appreciate the difference between the two, I would like you to look at the difference between two possible models of reality. One is you have a treatment which doesn't affect any individual. It's like placebo. The other one, a treatment which cures 10% and kills 10%. And the two are indistinguishable in experimental studies, in randomized control experiment. So here you have a model 1, drug has no effect whatsoever on any individual. Model 2, drug saves 10% of the population and kills another. If you look at the principal strata or the type of individual here, you can see here no harm for model 1, no harm, no benefit, just people who are immune here, people who are doomed here, and here the two cancel each other. So you have a low number of people who are immune and zero number of people who are doomed. Okay? So that you have cancellation here, and the two models are indistinguishable in randomized control trial. Yet they are different for decisions. Why? Let's look at it carefully. Who cares about the difference between these two models? Let's look at number one, the patient is caring. M1 is useless but safe, whereas M2 could be scary or lifesaver. Why is it scary? Because you have 10% chance of being killed because of the drug. It also could be a lifesaver because if the drug has some pain relieving properties, you would like to take it despite the chance of being killed. It may be a lifesaver. And also, who cares is the policymaker. Imagine that Model 1 give you zero population efficacy, and Model 2 may cause outrage if people find out by autopsy that a patient, a member of the family, was killed because of the drug. Could you imagine the reputation of the hospital or reputation of the entire healthcare delivery system? Policymaking should be very concerned about the difference between Model 1 and Model 2. And number 3 is a researcher. Because from differentiating markers, we can get to understanding the underlying mechanism. For instance, you can get a situation where for uh, people who are, say, left-handed people who are at the age of 30 to 40 have difference between the bounds that you get are different. Then you know there is something about this population that could be serve as a clinical marker that may reveal the reasons for the difference. So you have 3 levels of concern about the difference, about the probability of harm, probability of benefit, as opposed to probability of, say, probability of good outcome. In general, we know that the probability of benefit and harm cannot be point estimated, but they can be bounded. And the bounds shrink when both experimental and observational data are combined. Why? Because the intuition is when you have, imagine that M1 has no effect, can be ruled out if you happen to find no death in observational studies, as if people who are given free will to choose the drug have a premonition that they should avoid it. That it gives you an idea, or immediately rules out the model 1. And in general, the mathematics give you tight bounds on the benefit. So for every combination of clinical trial data plus free choice data, you can find the bounds, a tight bounds. What does it tell us? To appreciate it even further, I'd like to look at the concrete problem. Imagine that you have patients in the care unit waiting for attention or for treatment, and you need to choose any of them so as to maximize the overall societal benefit for the chosen set. And remember, the probability of benefit is the probability that the patient with characteristic C will improve if and only if treated. Here you have the formula for that. What can you say? How can you choose the set of N patients which optimizes the overall benefit to society? And in benefit to society, I include already the consideration of the hospital manager or the state decision maker. Well, I call it situation-specific decisions. In general, what does it include? It includes personalized medicine. By personalized medicine, I mean choose the right thing to do for this particular patient on this particular bed with this particular instrument and this particular scissor. All this should be can be taken into account, okay? And that's what I mean by personal medicine. What else? Identify customers worthy of offering or recommendation or special offer, a special incentive. Okay? So it plays an important role in the business world, in marketing. Characterize voters swayable by a slogan. I don't want to elaborate on the political ramification of that possibility. Or in general, unit selection, and this is a paper by Lee Muller that you can read at your leisure and gives you the conceptual basis for going from average treatment effect into a personalized treatment effect. Look, for example, what we need to do is the following. We have here the probability of harm plotted for both. Here are experimental data only, and here is the combination of experimental and non-experimental data. And you can see how things changes, despite the fact that they are non-recognizable. The different is not is not distinguishable in the experimental data alone. And now we have to make decisions. So we are we are estimating, a decision maker estimate utility function, alpha, beta, gamma, delta, attributes this to the various population here. And here you have alpha affecting the B, the benefit, beta affecting the harm, gamma affecting U, and now we have to combine it, and as we combine it, we have the utility of benefits, harm, and doomed, utility of every unit selected in the population, and now we can optimize it. I will go quickly and eliminate that, how to deal with bounds, okay? Because sometimes the bound disappears, and sometimes you get a conditions that for not here, for instance, we find a situation where men and women are indistinguishable in the experimental data, yet for women things are utility is positive, and for men is negative. So you can get a tremendous mileage by looking into the bounds. I will go now and summarize it with my conclusions now. Quoting a Harvard professor, it gives me the audacity to quote it. More has been learned about causal inference in the last few decades than the sum total of everything that had been learned about it in all prior recorded history. I don't know how I will get the audacity to be that sweeping, but if you are a Harvard professor, you can do it. But now that Harvard has crossed the line, I can add my little pebble. Medicine is on the brink of a major revolution. If we can now answer situation-specific questions that scientists have always longed to ask but couldn't. And this is the author, your humble author here, and advising you to read the book of why, and just saying one little element here that I was asked by readers what I propose to for the new administration of healthcare system, including the new administration of NIH, and I want to mention here that the person who is about to manage the new NIH, his name is Jay Bakatra, I believe his name, and he is not a bureaucrat. He is a causal reasoning researcher. I talked to him at length when he was one of the discoverer of bias amplification in economics. So, and he is adamant to change things around in NIH. And if it was up to me, I would advise him to look at 3 areas where NIH thinking ought to be changed. One is the fusions of data from diverse sources. It requires causal thinking, and I don't believe the current management of the current intellectual leadership of NIH is attuned to that possibility. And the second one has to do with causal diversity. I'm sorry. No. The last one has to do with personalized medicine, which I think we are ready. We have the techniques, we have the algorithms, and we have the theory behind it. So it will be, in my opinion, a major change in thinking in the next generation of healthcare systems. Okay, I would like to end up here. If you ask me a question about the recent popularity of large language model, I will say quite a few words. Thank you.
Thank you very much. I hope you can hear me. Yes, I think you can. For a great lecture. I think you would agree we would like to ask some questions or make comments, and I've asked Jamie Robbins, you mentioned him already, to be our first discussant. Would you agree with that?
Of course.
Great. Okay, Jamie, I think it's superfluous what I'm going to say now, but Professor James Robbins is the Mitchell and Robin Lafodi Professor of Epidemiology here at the Harvard School of Public Health, and he focuses for many years on causal inference approaches. Jamie, please, the floor is yours.
Thank you. Hello. Yeah. I'm going to do a couple of things. Well, first, my plan was just to ask Judea questions about what he thought about this brave new world, because I like his answers, but then I read his slides and then I decided I can't just ask him questions. I have to give him my point of view. But the question, but he's very good. The questions I want to ask him is, if we ever get to it, maybe later, is his view of what whether he ever expected a ChatGPT to be doing what it is some 5 years ago. Secondly, does he think free will exists? And do humans and computers have different kinds, or either? And then do only humans have subjective experience, or will robots and computers have subjective experience? So keep those in mind. But now I'm going to talk more about what he talked about. Just also, sometimes when I've been around today, he doesn't express things. He's saying things that are true, but not everybody's getting it, because I think we have like any discipline, we have a language. So the last stuff he was talking about getting more information. You can't make decisions from randomized trials, but you can find things out if you combine randomized trials with observational studies of the same population. Is to think about, to think about it in a simple way. What are you doing in a usual randomized trial? You're comparing the two treatment strategies: always treat and never treat. Those are the only two strategies you try. And now let's say you look at the observational data, and the mean survival in the observational data is overall survival is greater than either of the treatment arms than in the randomized trial. Well, we always thought randomized trials were best, but doing nothing turned out to be better. That's what he's talking about. What's going on there? What's going on is that there are a lot of other treatment strategies, and people can have private knowledge of their own, whether the drug's going to be good for them or bad for them based on other experiences. And so they're not doing the population is actually following a different regime. It's following an optimal treatment strategy, a better treatment strategy, not optimal, based on whatever their subjective knowledge is of whether the drug's good or bad for them. And so they do better than forcing everybody to take it or forcing everybody not to. That's what he's saying. And you can start seeing that in the data if you have both the observational data where people self-selected and a randomized trial. Like you could have 50% of people die in a randomized trial and no one dies in the observation. In an extreme case, which is what he mentioned. So I'm not even getting to what I want to get to. Okay, so now, because I think, maybe I was wrong, but I think that's the kind of thing, the way he expresses how we do. Okay, so this is how I started. When I gave the lecture, I was just saying, okay, we're in the midst of a causal revolution. And I would say, all these different disciplines, everybody who does causal inference, we all could understand each other, talk language. It's totally idiosyncratic 40 years ago. And so people learn a lot faster because there's fertilized. And I would say Jay is probably the single individual most responsible for this transformation. So that's pretty impressive. And then what factors led to it? And there are all these things like, end of historical suppression of causal language, the internet making cross-disciplinary learning quicker, personalized medicine, precision medicine. People want to know what to do. Tech companies want to make profits. All this depends on causal inference, and they're huge data sets. You actually might have enough data to try to do all this. And then the last thing is the development of causal graphs that offer non-technical users the ability to validly reason about subtle and complex causal systems. And that kind of causal graphs, directed acyclic graphs, were Judea, along with Spirides, Glamour, and Shines at CMU, were really the developers. And why does that work? Well, causal graphs pretty much basically represent the way humans, including scientists, mathematicians, encode causal language. You all see a causal graph, you kind of know what those arrows are saying. And direct, indirect effect, you see it all. But also, and this is what Jay is famous for, is almost magically, as he says, causal graphs plus deseparation turn a difficult mathematical problem into one of simple graph topology. You just trace paths and see if things are deseparated. And if you were to do that mathematically, it would take hours. Even somebody completely trained. I mean, it's truly remarkable. And this has revolutionized causal thinking in many fields, including ours, precisely because almost anyone can understand the concepts, colliders and all this stuff, that before you would have had to have a lot of mathematical ability. And in fact, I'm going the wrong way there. And okay. Now the next thing, and so I'm even mathematically sophisticated people all use causal graphs to reason also. Now, then I was going to talk about Judea's graphs versus Swig's, but I may not have enough time. I always wonder why he doesn't like them, maybe because he didn't invent them, but who knows, maybe he actually has a reason. Okay, so, but the bigger question, because this is, I'm not going to get into the subject that all us have to do now is just fight with Judea about. And this is, so I'm going to take you through my history because you'll see the relationship in a moment to a slide he had. So, when I first started this in the early 80s, no one even know how to formalize what's the meaning of the causal effect of a time domain exposure when there's, mediators and feedback and so forth. And so I wrote this. This is taken from my addendum to my long 86 paper. Is I was saying, okay, so you get data, you get a lot of numbers from empirical measurements, and after they do some calculations, the person who drew the data says things like my analysis shows strong evidence of a direct effect of formaldehyde, mortality not mediated by cigarette smoking. So the relationship, they got this data, they did all these calculations. So what was the relationship between the final English sentence and all those calculations in the computer? And because the things in the computer are clearly well-defined, mathematical, very precise. So you would think it would be important to provide formal mathematical definitions for the English sentences expressing the investigator's causal inferences to connect it to the calculations being done. And that's what I tried to do in my 86 paper, and to create this causal model, okay? And then the kind of questions, so Judea at the start gave some of the kinds of questions that before there were these kind of formal causal models, it wasn't clear how, what even you were saying, that what would you do with data to answer these questions that people naturally ask, like these ones. I'll focus because this is what is the the obesity issue, okay? But so as I agreed with him, that's what I was doing, that before having these causal models, you couldn't even articulate in the standard grammar of science what you were trying to do and why you did the calculation you did, okay? And basically, the model I had in Judea are basically isomorphic I mean, there's subtle differences, but that's not the level I'm interested here. But the difference is when the way we think about it is that when people say these English sentences, it wasn't like I just wanted to map them. I wanted a theory so I could say to this person making the English statements, I don't think you know what you're talking about. You don't even know what you're asking. And that's still a major part of what we, in epidemiology, me and Miguel and other such people, think we're doing in causal inference. And so, so I'm not worried about whether it's a things about the causal effects of obesity. So under either of our formal theories, mine or Judæus, which are really similar, if you put obesity on a causal graph, you're implying, because we have this counterfact, you know, all the counterfactuals about what would happen if you changed obesity, that, you know, that the causal effect of obesity is well defined, even if it's not identifiable from the data. But the graph says, you know, I think I know what I'm talking about, or someone does when I put it on the graph. Why isn't it moving? Begin. Stop moving. Well, I'll go on without it. I don't know why it's not moving. Anybody knows. So okay, so the point I'm trying to make here is I think we come from very different backgrounds. And his point of view, which he hasn't sometimes articulated, is interesting. He says, look, I'm just the poor, you know, causal expert. I go to the subject matter expert. Subject matter expert tells me what they want to do and about obesity, and I take their expertise as a given that that they know what they're talking about. I put their variables on the graph. They say, "Oh, I know what obesity does this," and it's up to them to make sense. I'm not the subject matter expert; they are. Our view, I think, because we're actually involved in real world studies and stuff, is quite different, which is to say, if you don't know what you mean by the causal effect of obesity, don't put it on the graph. You may be the subject matter expert every bit about obesity and the chemicals and the reactions and so forth, but you're not an epidemiologist. You don't know the relationship. You're not an expert in how to go from concepts like obesity and so forth, gotten in data, you've done a study, you have data, what do you need to believe and know to link that? And just saying, I'm saying there's something I believe in called obesity, like, what does it mean to change your obesity? I mean, so there's this whole, so we focus a lot of our energy on telling people, trying to clarify to people, what the hell are you talking about? Do you think you know what you're talking about? And working with them to get them to realize what can be done with data and how that may relate to their substantive concerns when they're, you know, biochemists who are thinking about reactions, but they have to give me logic data.
Jamie, shall we ask
Yeah.
Judah to
Okay.
give a comment on that?
Okay. So anyway, we don't like to put things on the graph that he does. And we're fired on that. We don't like to put arrows now. We don't like.
You can unshare this. Okay?
Really just wants to talk about free will.
Judah, any response from your side? You can unmute yourself. Does it make sense what Jamie said?
Can you hear me?
Yes.
Okay, two comments. Number one, Jamie, please send me a copy of your slides because I need them to defend myself against the last remaining islands of resistance.
Remaining.
And the second one is about obesity. I welcome you to read the paper which I wrote about this very issue, claiming that the effect of obesity is well defined and defined by the graph. And the title of my paper is it obesity or is it the soda? And I can send it to anyone who wants. Just look under soda and you'll find it. So the effect is well defined given the graph, even though you cannot directly manipulate obesity.
All right. You're working here. Would you like to go into the general questions that Jamie started with, Dr. Pearl?
What are the general questions?
Jamie, can you repeat them?
The is there free will?
Yeah, and also what.
That was one.
First, also success of what ChatGPT has been able to do compared to what anyone thought such a thing would happen in the last 5 years. And then issues about free will and subjective experience and robots versus humans.
About free will, it is an emergent phenomena. We don't have free will when you're talking about a robot. A robot can only do what he or she was programmed to do. So when we talk about a robot, we definitely we are dealing with a deterministic system to all practical purposes. And still the question is, should a robot be programmed to believe that he or she has a free will? Does it have any survival value? Once we understand it, and I think it has survival value, I have outlined a few of the benefits, computational benefits that come from the illusion of free will in the last chapter of the book of Why. So once we understand the computational benefits, we can also understand how to engineer it. And the answer is yes. Robots should be programmed to believe in the illusion that they have free will. I'll go now to the chat GPT. It's very important. The whole constraints that the ladder of causation puts on the analysis falls apart when we are dealing with systems like LLMs, which are driven by text written by individual authors who do have causal opinion, causal model of the world, and we are extrapolating their individual perception of the world. So we are no longer constrained to say you cannot go from level 1 to level 2 because or level 2 to level 3 because the author of the text had a level 3 ideas about the world. How to deal with, now we are talking about a new science, essentially. How to prompt the LLM in order to provide us with a reasonable extrapolation of the text. Right now we get a salad of rumors, which we need to rein in and understand. And this is a question that many people are working on, under what condition we can predict and or believe that the outcome that comes from the salad of rumors has a validity in the world.
Thank you very much.